So this presentation is 2 hours. We really need 2 hours to make it. We called it a masterclass because it's as much about education as it is about research. In particular, in the first part, we are not going to talk about our latest research on machine learning for pricing, but we are going to review some very classic and well-known notions about it. So hopefully you will find that useful, but also it will help us establish a formalism, some notations, and a context that will make it a lot easier for us and hopefully for you for the second part, where we will be talking about new things, latest research that Brian and I have been conducting in the past year. So I see that we have some of the brightest minds of the industry here. Hi, Jim. So yeah, we don't expect you to learn much in the first part, but bear with us. We will make it up to you in the second one. So, let me get starting here with what it means to be pricing with machine learning. And since we are going to learn pricing functions with artificial intelligence, let me start with a famous example where it was performed by human intelligence. I'm talking about SABRE. 20 years ago, Pat Hagen was given the specification of a stochastic volatility model that later would be known as the SABRE model. And his task was to find an efficient computation for the price of a European coal in that model. So famously, Pat locked himself in a room for a few days, and then he came out with a SABRE formula here, scribbled on a napkin, and the rest is history. So let me just make a few comments that will be important for what follows. Pat was not looking for a good model. He was not looking for the most realistic model or the most effective model. In fact, the model was given to him. He was only looking for an efficient computation in the model. And when I say only, of course, it's between quotes, because this efficient computation made all the difference. It effectively brought stochastic volatility to trading desks. Another comment is that this work was in one particular model, SABRE, with one particular financial product, the European coal. Actually, a few months ago, in Risk Magazine, Pat published another formula in SABRE for the constant maturity swap, or CMS, 20 years later. And this is, of course, a completely separate piece of work. So which begs the question, can we design, one implementation that will work for arbitrary models and arbitrary instruments? So this will be a major theme in this presentation. And obviously, Pat cracked the SABRE formula with mathematics. I'm only mentioning this because machine learning, as we all know, doesn't work with maths. It generalizes from examples. And finally, something that I need to mention now is that this formula, Pat derived it offline once, and then it was reused forever. Pat invested considerable skill and effort and time into it, and it was time well spent because subsequently the formula was reused like trillions of times on trading desks around the world. But if I'm deriving a formula just to use it a few thousands of times, then maybe I can't invest that amount of effort into it. And so what we want to do in this story is to replace Pat Hagen with a machine, and such that if I show this machine any pricing model, a risk-neutral model of some dynamics combined with the arbitrary derivative instrument, this machine will be able to find an efficient approximation, an efficient computation for the pricing function, which is, as we all know, the expectation of a final payoff conditional to the initial state. One word about application. I want to do that not only for sport. I mean, it's pretty cool that we get to program our own synthetic Pat Hagen, but there are some real stakes in that story. Investment banks in particular need to calculate a lot of things like risk heat maps, calculations like XVA, CCR, etc. And all these things, what they have in common is that they will value the same derivative transaction in the same pricing model many times in different scenarios. And one number maybe to keep in mind is 10,000. That's typically the order of idea of how many times we need to evaluate the pricing function in different scenarios in a typical risk computation. And you know, in general, a fast evaluation like with analytics or expansion Salas-Seber or things like numerical integration or finite difference methods, that's only available in restricted cases. The only method that's always available to me is Monte Carlo, and that's notoriously slow. And so there will be a massive computation cost for all these things of around 10,000 pricing by Monte Carlo. That's the order of idea. So what we propose here is to invest some time learning a fast computation and thereby saving us the cost of these 10,000 Monte Carlos. Which means that my pricing function, I will learn it once and then I will use it around 10,000 times before I discard it. And again, it only makes sense if the cost of training is, well, much less than 10,000 pricing by Monte Carlo. If it costs me the same time as 1 million pricings by Monte Carlo just to learn the pricing function, then I may as well go and do everything with nested MC. So we are going to see that we can do it in around 5 to 10 pricing by Monte Carlo, thereby giving us a speed up of in the thousands. And that makes all the difference between, you know, performing these computations overnight in data centers and, you know, pray that it's completed by the morning, or being able to do them in real time on trading workstation. So this is what it's about, the application, and that very clearly tells us what the constraints are. Because my learning function will be learned online, and it will be disposable, which means that I will, the learning of a pricing function will be part of a risk calculation. And it will be learned in that context, in the context of one particular calculation, and used for this calculation only. And so really, I have a limited budget for the computation cost of this whole learning process. Then, of course, machine learning learns from examples, and we want something that works with any model and any derivatives instruments, and importantly, including netting sets or trading books, basically collections of multiple instruments. But really, the main context is the same, is that we are not trying in this story to learn a good model. We are given a model, and we want to learn a good computation in that model. Okay, so this is the big picture here. We are given a pricing model, a derivatives instrument. We are going to train a machine learning model. We know we have to do it in reasonable time. That will give us a fast pricing function, and we will evaluate it repeatedly to compute all kinds of risk metrics. So let's start with a pricing model. What do we mean exactly by that? Well, usually a pricing model, we think of a probabilistic description of a risk-neutral dynamics of some market state variables. So for instance, a one-dimensional diffusion a la Black-Scholes or Dupere, where the state is the price of the underlying asset, and so it's a state in dimension 1. Of course, we have extension, multi-underlying extensions, where now the state is given by the price of n different underlying assets, and that's in dimension n. Stochastic volatility models a la Seber or Heston, where we have a two-dimensional state, that's an underlying asset price, and it's instantaneous volatility. Yield curve models, a la LIBOR market model like this. This is interesting because the state in LIBOR market models is given by all the forward LIBORs on the yield curve. So for instance, if it's a 30-year problem and you work with quarterly LIBORs, you're in dimension 120. So this tells us that the kind of dimensionality that we face is often in the hundreds, not 1, not 2, not 10, in the hundreds. And of course, for multi-asset hybrids or regulatory like XVA, we use high-dimensional models, which are essentially a consistent assembly of multiple different models. And so the state will be a concatenation of all the underlying model state, and the dimension will be the sum of the underlying dimensions. So because we are building a general machinery, we need an abstract definition of a pricing model. And instead of a math definition, what's convenient for me in this presentation is to give you a computer science definition that I will work with. So I will say that a pricing model is a function, I call it f, and this function takes two arguments. It takes an initial state in dimension n, which I call x, and it takes a collection of random numbers, d uniform random numbers independently picked in 0, 1. And d is the Monte Carlo dimension. That's how many random numbers you need to build one path, okay? And what this function does, it simulates a path for some state vector under the risk-neutral measure with the initial condition and the random numbers that you give it as an argument. So a model is a pricing function here. So for those who are used to reason in this kind of format, you will notice I took a shortcut here because my definition assumes not only a model but also a discretization, a simulation scheme for that model. So for the definition I will be using here, we have a model together with a simulation scheme, maybe Euler, maybe Milstein, maybe random grids, that doesn't matter, but you have a simulation scheme for it. And so a model is really a recipe for the simulation of risk-neutral paths. So function, you give it an initial state here, you give it some random numbers, and it simulates a path with these random numbers. So this is the pricing model. What about the derivative instrument? Well, derivative instrument is a functional of a path. It is described by a term sheet, and the term sheet tells us what cash flows are paid or received under what conditions. So really, a derivative transaction is a functional, which I call J. You give it a path as an argument, and it returns the sum of discounted cash flows evaluated over that path, also called payoff, of course. And note that this definition also covers trading books simply by aggregation. The functional of a trading book is simply the sum of the functionals of its underlying trades. At first sight, it may seem like things like early exercises are not covered in this definition. Actually, they are. And to convince yourself, you can think of a classic Longstaff-Schwartz algorithm. What it does, essentially, it's a pre-processing step that will turn early exercises and things like that into path dependencies, and path dependencies are trivially covered in this definition. So everything so it really covers everything, maybe modulo pre-processing by Longstaff-Schwartz. So maybe it gives me one opportunity to shamelessly advertise my latest book with Jasper Andreasen, fresh off the press with Wiley last month. And it's about scripting and how it's applied in derivatives pricing, risk management, XVA, and this kind of stuff, because we believe that the best way to implement this notion of a derivative as a functional is with cash flow scripting. Basically, it frames the term sheet as a smart contract by a computer program that executes the term sheet and computes this functional G given a path P. Okay. So actually, there's a detail here that is not without importance for a practical implementation. And this detail is that it's correct to say that a derivative is a functional of a future path, but this is only correct at launch when we issue the derivative. But if we must handle it throughout its lifetime, then the derivative transaction will carry a state, and that state is distinct from the market state. For instance, if you think of a barrier option, at some point of time, it may be alive or dead, which means that it carries a state which is either 0 or 1, or if you use smoothing, a number between 0 and 1. So something, a physical swaption may have been exercised into a swap or not. And an Asian option, another example, it's an option on the accumulated average. So it doesn't only depend on the average to be accumulated in the future, but also on the average that has been accumulated so far. And so it carries a state, which is the average that you accumulated over the past path. So in general, a derivative is is a function g, a functional g, that takes as an argument not only the future path, but also the initial state of a transaction, which I call xi, in some dimension ni, and that's the collection of all the necessary path dependencies. So we defined the model as a function f and a derivative as a functional g, and we will be working with the composition of both of them, which is this function h. And this function h is simply, the functional g applied to the result of f. That's what it is. So it takes as an argument the initial state, both the initial state of a market and the initial state of a transaction, and it takes a random number, a random vector that it will use to simulate a path. And it returns, and it will construct a path internally and evaluate the payoff over this path. And by the way, I will work with a concatenation of these two things, the initial market state, the initial transaction state. I will just call it the initial Markov state, the concatenation of the two in a dimension which is the sum of the two. Okay. And in other terms, a model is not a model. The pathwise payoff function h is a recipe for the simulation of payoff. So you give it an initial state, a random vector, it will simulate a path, and it will read the payoff along that path. That's our function h, okay? And because it's so fundamental for what follows, to bring this point home, would like just to show you how it plays out in Black-Scholes for European call, the simplest possible example. So the payoff is x capital T minus k plus, x capital, that's the functional g. By the model f, the x capital T is a geometric Brownian motion starting in the initial state x with a random number given by this w. Yeah? And so if you just take this guy and substitute it in there, you find the h function in the Black-Scholes model. It's like this. I also show you below how it plays out on maybe a slightly more complicated example of a barrier option. I'm not going to go through it, but if you want, if you want to review the slides at home on your own time, you can review it. The point here being that for any product in any model, you have a formula. Maybe it's very long, maybe it's complicated, maybe it's unsavory, but there's always a computation, h. This h is always defined. And so we have our model, we have our transaction, and we have this pathwise payoff h, pathwise payoff function h, which is the composition of the two, and we want to learn a fast pricing function. And if we denote y is equal to h of x, we know that our pricing function, v of x, is just the expectation of y knowing x, the expectation of the final payoff given conditional to the initial state. And so that's just the integral of our function h dw. You integrate a randomness out of the payoff. That's how you get the price. And of course, you can compute it by an approximation with a discrete sum, whereby every time on every term of a sum, the initial state is the same, but you're using different random numbers to integrate them out. You can pick them randomly or more intelligently with a sequence like Sobol. And this is, of course, what we call pricing by Monte Carlo. And it's slow because it converges slowly, so you need a large number of simulations, a large number of terms in this sum. And remember that each evaluation of h takes a simulation. Simulation of a path. So instead, we want a fast pricing function whereby we will approximate this function v by an approximation alpha, which is also a function of x, subject to a vector of parameters theta. For example, it could be a regression, and that's just reverts to the classic Longstaff-Schwartz algorithm of 2001. That's if your approximator is a combination of fixed basis function phi k with a coefficient given by theta k. Another example could be a neural network where these thetas are the connection weights of a neural network, and you evaluate this function alpha by feeding the input x into the input layer and computing an approximation of a value in your output layer. And that was done, for instance, by Lapper and al. Last year. So as I said, really nothing new here, okay? And we want to train a machine learning model now on to give us something like that. And to give us a fixed budget, we are going to give ourselves a budget of 10 pricings by Monte Carlo. So we want to train our model in less than 10 pricings by Monte Carlo. That's our goal. So let's zoom in. What does it mean to train a machine learning model from a pricing model and a derivatives instrument? Well, we're going to do it in two separate steps. First, we will simulate a data set, and then we will train the machine learning model on that data set. And again, the combined cost, we want to be less than 10 pricing by Monte Carlo. So let's start with a data set. A natural approach could be to do something very classic in a supervised learning approach, whereby we learn a function v of x, where x is the initial state and v is the price in that state, from a training set of m examples, where I will show the machine the ground truth price. So each training example will consist of an initial state xi and a label yi, which is the value function in that state. So this is an interpolation problem, because I'm going to give the correct price on a certain number of nodes, and I will want the machine learning model to generalize to out-of-sample examples. That's the approach, for instance, that Blanca took in the context of raw volatility 2 years ago. And it's kind of obvious that it will converge to the right pricing function as I increase the number of nodes. But it's also obvious that it requires many training examples, at least thousands and up to millions. And that means that it's not going to fly for us, because we want to do it in less than 10 pricing by Monte Carlo. But if we do it like this, well, the data set simulation alone will take a computation cost of at least thousands of pricings by Monte Carlo, because, you know, all these ground truth, I will have to compute them. And so this is not going to fly. So instead, we are going to do something different in the spirit of the original paper by Longstaff-Schwartz, which means that we are going to learn the value function v of x, not from ground truth prices, but simply from a training set of m payoffs. So now my training inputs will be x of I, the initial states as usual, but my training labels will not be prices, it will be payoffs. Computed with this function h that was defined by my model and my derivatives transaction. So the label will simply be a payoff computed with this initial state and some independent random vector wi. And this is no longer an interpolation problem, this is a regression problem in the spirit of the original LSM paper, whereby we learn prices from payoffs. And remarkably, I will show you shortly that it still converges. And, but now, each training example is computed for the cost of only one pricing by Monte Carlo. And so the whole training set is computed for the cost of m paths, which is similar to only one pricing by Monte Carlo. And that's the key. So now we know what our simulated data set looks like. It looks like this. I pick some initial states xi, and I computed the label yi with this function h, evaluated in xi with a random vector wi. So we know the data set. Now it's about, you know, training the machine learning model. So which means, again, an approximator alpha subject to some parameters theta, which is meant to approximate this pricing function, which is itself is the integral of h dw, which brings us to the second part, which is to say how classic conventional machine learning algorithm play out in that context.
Yes, and now that Antoine has set the scene for why we want to do this, then we're ready to go into some more details. And first of all, we need our data set, and for that we need m independent realizations, xi and yi, of random variables, x and y. So the goal is to learn the pricing function, alpha, of the input x and some weights or parameters, theta, and that should be close to the value function x, which is the conditional expectation of y given x. The definition of the conditional expectation is given here, and that is actually the function of x which minimizes the L2 distance to the stochastic variable y. And the mean squared error estimator is this finite sum. So it's important to note here that the minimization criterion must be the mean squared error and nothing else. Otherwise, you'll converge to something which is not the price. You'll have a bias. The approximator alpha is universal when it spans all functions of x, when the capacity goes to infinity. So, for instance, polynomial regression is universal for smooth functions. Since all smooth functions, they are combinations of polynomials. Other basis function regressions, such as Fourier and spline regression, are also universal. And there's a universal approximation theorem for neural networks that tells us that that is also a universal approximator. And that's been talked a lot about that recently, and maybe a bit too much. Often life says that, well, every approximator is more or less universal. So this is, and it's not really that mysterious that this universal approximation theorem, because if you consider a one-dimensional ANN with one hidden layer, which is ReLU, then we have this sort of function, which is a linear combination of call payoffs with different strikes. And then the universal approximation theorem tells us that this sort of function can represent any function, and or that it can be decomposed over all these hockey sticks, or this hockey stick basis. But we already knew that from the Carr-Madan formula, that all European profiles are combinations of calls. And even in that case, they give us the weights or the thetas we need explicitly. And this is the basis for static replication of variance and CMS swaps. So if we put it all together, the fundamental theorem of ML pricing is a universal approximator trained by minimization of the mean squared error over a training set of payoffs a la LSM converges to the correct pricing function. And this is, well, for some it may be trivial, but I think it's not that trivial, and it's somewhat non-intuitive, because really a machine learned model trained on payoff data converges to the correct pricing function, despite it has never ever seen a price. So it's kind of like this cloud of points. From this cloud of points, we learn this pricing function. So can we really do that? That's amazing. We have an example here with Black-Scholes. It's a 5-degree polynomial regression on the Black-Scholes, and on the x-axis we have the spots, and on the y-axis we have the cash flows and the prices. Then going left to right, we have more and more training examples that we train our regression on. So we have 1,000, 2,000, and 4,000. And you can see more and more cyan dots. The cyan dots, that's the training samples. And the blue curve, that's the regression. and the one that we are after, the prediction function. And then the red curve, that's the closed form solution for the Black-Scholes formula. And as we can see, more and more training examples, and we get better and better. We can see that that the blue curve is closer and closer to the red curve. And you can reproduce all these examples that we have in the presentation and in the papers by going to this GitHub repo, and you can also use it in Colab, or open it in Colab and run it on your browser, so you don't have to install a lot of stuff. The Black-Scholes example is not really representative because it's one-dimensional. And as Antoine told us, it's typically high-dimensional problems that we are facing in finance. For instance, the LMM or the labor market model example, where you had a dimension of 120, or netting sets, or where you generally get over 100 input variables. So a more representative example could be a Bachelet model with, since this will end up with an analytic solution, so it's equally simple, but more importantly, it's multidimensional. So the input state, x, is a number of spots, say n, and then we generate an n-dimensional path by this formula, the input, or the initial state plus the correlation and the Gaussian noise, or the Cholesky of the covariance. Then we get a cash flow for a call on this basket by taking the call payoff on a fixed weighted basket and a strike K. Then we have our payoff, that is this function down here, where we put in the x at expiry with the initial state or the path, generated path formula. So that gives us an analytic solution, of course, because it's just a fixed weighted set of Gaussian variables. That's again Gaussian. We can use the Bachelet formula. So let's see how that plays out. Here again we have the same sort of pictures. This time we have 4,000 training examples in all of them. But going left to right, we have more and more, or higher and higher dimension, 1, 3, and 5. So the first one is pretty much the Black-Scholes example, where we have a one-dimensional variable, and in this case it's Gaussian. Before it was log normal. But it's the same sort of picture. And as dimension increases, you can see that the blue dots get more and more, becomes a cloud really, and the red curve is the one that we are supposed to fit. So in dimension 5, it doesn't really look all that great. And why is that? Well, that's because of something called the curse of dimensionality, and that's because you get more and more basis functions. The more and more basis functions, you get a lot more parameters that you need to find. And if we think about it in a cubic regression, then you have, for the dimension 1, you only have 4 coefficients that you need to find. And dimension 2, you have 10 coefficients. And then it grows and grows, and it grows with n cubed. And if the degree is something else than 3, then it grows with n to the power of p. So that gives us a lot of coefficients. And the regression really overfits the noise to this specific training set, and it ends up really interpolating all this data. And that's really not what we want. We know that we have We have noise in there, so we really don't want to fit all the points exactly. Yeah, and this really goes for all sorts of regressions. It's not just polynomial regression, also Fourier and spline regression gets hit by this. And really it makes regression not usable in real-world problems like we are trying to solve here. So how can we get around this curse of dimensionality? Well, one approach is to stop the optimizer from really trying to interpolate all the points correctly. So you regularize the optimizer and kind of put something into the cost function so that you don't. We'll see that. Well, we could also reduce the dimension before the regression, and that could, for instance, be done by PCA. And we could also try to find the most important or the best basis functions, and that's really what artificial neural network does. So we'll also try that. And we'll go over these three methods and see to see that the regularization, it kind of works, at least in low dimension. PCA, it does not work, and it is actually unsafe and should never be used in this context. ANNs, they're effective for offline learning, but online learning, as we want to do, takes too many training examples, so it's also a little bit of a problem. And then finally, we'll see how to resolve all those problems. The regularization. The regression model looks like this. So you have your weights and your basis functions, and then you have the cost function, which was the mean squared error. And then we know that classic regression has, this is a convex problem, so it has a unique minimum, and the minimum is given by this solution where you have the inverse of the covariance matrix with the basis functions and multiply that to the covariance between the basis functions and y. And the covariances will be estimated over the training data. The Tikhonov regularized regression penalizes large weights. And so you add this term here so that large weights will be, you don't want that in this sort of regularizations. You prefer solutions that has lower weights to solutions that have large weights. And the good thing about adding it, the error term with the square, that is that we keep the analytic solution and we really just add the lambda to the diagonal of the covariance matrix before inversion. So this constrains the optimizer to prevent it from overfitting the minimum mean squared error on the data set. But now we're no longer minimizing the mean squared error. And that was exactly what I said before, that would actually give us the correct value function when we did that. So we're no longer doing that, so this introduces a bias. And also, the performance of this sort of method strongly depends on this parameter lambda. Because if you have 0 lambda, then you end up in the classic regression case, and that's where you have the overfitting problems. And then you could also have a really large lambda that basically sets all the weights to 0. So you really predict the average y. And that is what is called the bias variance trade-off, that you have this trade-off between a high bias and a high variance. And therefore, there must be somewhere where there's a sweet spot, and generally that is found by cross-validation. But this is expensive with nested optimization, and it's a waste of data, really. But here we have an example of it. And in this case, we have, again, it's the basket, dimension 5. We have a polynomial regression, degree 5, and 4,000 examples we are training on. And on the left, we have the classic regression, lambda equal to 0. On the right, we have a high lambda, lambda equal to 10. And in the middle, we have something which is the sweet spot, or found by cross-validation, with a lambda of 0.76. And if we compare this solution to the classic regression, that was this one here, then we can see that the blue points are no longer as spread out. They're tighter to the red curve, and that means that the variance is less. But then we can see that there's a bias, because the red curve is below all the blue points at the top, and we have a little bit more blue points below at the middle. So we can see that it introduces a bias, but it decreases the variance compared to what we had before. But really, we know that in this particular case, we know that this is really a one-dimensional problem. So why can't we make it look like the one-dimensional case? That's a bit frustrating, and we would like our method to figure that out on its own. But it's still worse than that, so you have to be here for the rest of the presentation. So in high dimension regularization, we'll have a problem like regular regression, because you have this solution to the problem where you have to invert. This is a matrix, and the matrix is a K by K matrix, where K is the number of basis functions. And to take quite a large example, then degree 5 polynomials in dimension 20, that will give you 52,000 basis functions. That's a big matrix to invert. So it's practically unfeasible in dimension above 10. So instead you could use gradient descents or variance of it, but it becomes very expensive with cross-validation and nested optimization. Other regularization methods, lasso is one, and the difference here is that we have, instead of having the parameters squared in the cost function, we have the absolute value of the parameter in the cost function. So again, this will also be biased, but on the good side for this sort of regularization, on the minimum, lasso sets most weights to 0, so it kind of says which basis functions it likes the most for this specific problem. But it's not really a method that we are using, and the ANNs, as we'll see, also perform feature selection, but in a more effective and general and principled manner. Another regularization I just want to mention briefly is the derivatives regularization. It's where you, in your cost function, put in the, for instance, the square of, say the square of the second order derivatives of your function, and that means that you kind of prefer linear functions, because high second order derivatives, you apparently don't like that for this sort of problem. And that's also a little bit random, to put in there, but we just want to mention it because it, in some ways, it looks a bit on the surface as what we're going to present next, but it's really not the same at all. For differential machine learning, which we're going to present in a little bit, we'll penalize the wrong derivatives, not just because they're big or something like that. The derivatives regularization here, this one, that'll introduce a bias, but the differential machine learning that we are using does not do that. So there's significant differences. To conclude this, it does a decent job in low dimensions. It introduces a bias by construction, and that forces the cross-validation, and it is impractical in high dimension.
Yep.
Then it's you.
So recall, we are still in the classic framework, right? Absolutely nothing new so far. We are just reviewing classic machine learning and see how it plays out in the context of derivatives pricing. So I'm going to do the very last slice now, and then we are going to move on to current research. So Brian just talked about one possibility to mitigate the curse of dimensionality, and that's regularization. I will mention a new one, another one, not new at all, different approach, a natural one, which is, well, if regression works in low dimension but not in high dimension, shall we not then try to reduce dimension and then perform a regression in the reduced dimension? And the go-to algorithm in conventional machine learning for dimension reduction is PCA. As you know, the principle is we are going to reduce the dimension of X from n to a lower dimension p, and what we are going to do, what PCA does, it rewrites the n coordinates of X in a rotated basis where coordinates are uncorrelated, which is the eigenvector basis of a covariance matrix of X, which I denote CXX. And then you can measure the variance of the n coordinates of X in the rotated basis, right? And this is measured by the corresponding eigenvalues. And then you can just, truncate the axis where coordinates have a very low negligible variance. So this is PCA, whereby you will be locating your point X by only P coordinates and with minimal distance to original. So just to recall this, how it plays out, say, for two correlated assets, X1 and X2. So we have a cloud of points. Each point is an example in my data set. And I have X1, the price of a first of a first asset on the horizontal axis, X2, the price of a second asset on the vertical axis. And this is in a standard basis, and I can measure the covariance, the variances and the covariances of my examples. But then, of course, I can rotate the coordinate basis. And as I do that, you can see that X1 and X2, they change, the variances change, the covariances change. But there's, by a well-known property of linear algebra, what we call the total variance of X1 plus the variance of X2. This is invariant. So in the eigenvector basis of CXX, in a special rotation, if you like, correlation will be by construction 0, and the variance of X1 will be maximized, that corresponds to the biggest eigenvalue, and the variance of X2 will be minimized, that corresponds to the lowest eigenvalue. And then PCA reduces dimension by, truncating his rate coordinates, and therefore locating each point by only its coordinate on the blue axis, so by projection, basically. And you can see that this is what minimizes the reconstruction error. That's an equivalent way of formulating PCA, is how can you project your data on only one axis or only p-axis while minimizing the projection error. So that's what PCA does. But let's look at how it performs. In our example, our friend, the Gaussian basket, And no, let's not do it. Let's, to avoid boredom, let me show you a different example, a real-world example. That's the continuation value of a Bermudan option, actually a twice callable Bermudan option on the first call date, which means that now what I'm trying to price is a swap plus a European swaption, okay? And we'll be doing that in the 5-factor Gaussian model. So for those of you who are familiar with these things, we use the 5-factor multi-factor Chayet with a normal volatility specification. The data set was simulated in Danske Bank's Superfly. So that's our, basically our valuation and risk management system. So again, X is the initial state of a curve, in this case in dimension 5, and Y is the sum of the discounted cash flows until either maturity or early termination. And the example that I will show you, even though the data set was simulated in our proprietary system, I made it available, the data set, not the simulator, and you can run all these examples by yourself. You can play with the code. You have an implementation in Python. You have discussion of practical implementation details on our GitHub repo. It's called Differential Machine Learning, and you get all the details in this notebook. So this particular notebook is Bermudan5f.ipynb, and it's been designed to run in Colab. So again, no installation. You run it in your browser, on your iPhone, on whatever you want. It will just work. So now I have this data set in dimension 5, and as before, I will perform a polynomial regression of degree 5. This time I have 8,000 training examples, and after I train my regression model, I will measure performance over 128 completely independent test examples. Okay, that's how I will measure performance. So on the horizontal axis, I have a ground truth price in this 128 examples, and on the vertical axis I have predictions of my regression model, and so the error really is measured by the distance to the diagonal, and you can see that it's not completely ridiculous. It's sensible overall, but you still get some large errors, and that's pretty much the same picture that you got for the Gaussian basket in dimension 5, so no surprises here. We know that in dimension 5 a polynomial regression does not perform well. And by the way, we could marginally improve all that with regularization, but the point here, what I want to try with you here, is to reduce dimension with PCA. So let's see how PCA plays out on this data set. PCA tells you that the first component, so the major axis of variation, by itself explains 96% of the variance, and the second one, 3.43. So really, the first two components, they explain more than 99% of the variance together. So you could say PCA tells us that it's okay to truncate the three remaining components that were irrelevant. There's no variance, nothing happens there. And in particular, the fifth component, it's not easily readable, but the fifth component explains only 0.0047% of the variance. So that's completely negligible, okay? And so PCA tells us it's okay to truncate. And once I truncate, then I can represent my data set in dimension 2, not 5, 2, by projection on these two principal axes. And then I can train my regression model in lower dimension. I can train it in dimension 2 using the projected data. And then when I do a subsequent prediction, I have an example, a test example in dimension 5. I again project it on the 2 or 3 first factors and evaluate the learn function of the projected data. So that should work, yes, but no, because if you look at this graph, so this on the lower right corner, it's the graph that I already showed you, so we don't do any truncation, right? On the upper left, I'm doing my regression in dimension 2, the one that PCA told me it was okay to do, but it's not okay at all, because now the predictions are a lot worse. Actually, they're pretty random. And even if I truncate just the fifth dimension, if I truncate just this guy here, which is definitely okay to truncate, I get this picture here, which is much worse than this one, okay? So Actually, despite what PCA tells you, you cannot truncate anything here, because if you do, you can no longer learn the pricing function. Despite the negligible variation, you're removing some super important information from the data as far as this Bermudan option is concerned. So for a detailed analysis of what's really going on in the Bermudan example, we have a long discussion in the notebook. I really encourage you to look at this notebook. It's pretty interesting what's going on there. But here in this presentation, I would rather explain you what's going on in a much simpler example. So remember our correlated data set x1, x2. And now let's consider a spread option, an option on x1 minus x2. Right? So a spread option, it's like a basket with weights 1 and minus 1. And so in a Gaussian model, which is what I use to simulate this data set, in a Gaussian model, we know that it depends only on the initial basket, so x2 minus x1. So it's really a function of the initial basket, and you can see that very clearly by just computing the gradients of your pair of functions with respect to x1 and x2, and you can see that they're all completely aligned with the anti-diagonal. Of course they are. They're all proportional to x1 minus x2. And so gradients are all aligned in the anti-diagonal, but PCA truncated this anti-diagonal because there's no much variation going on there. Well, yeah, that's nice, but then you can see that the gradients in this case are almost aligned with the truncated axis, so this axis may have low variation, but as far as the spread option is concerned, this is where all the actions takes place, right? Because the projection of a gradient onto the blue axis is virtually zero, so nothing happens. So the spread option doesn't at all depend on that coordinate that PCA thinks is important, but in fact it's not important at all. There's nothing happening there, no action. So in fact, yeah. And so by truncating effectively the only axis that really matters for the transaction, you're losing all hope to ever learn any meaningful pricing function for your spread option. You can forget about it. So this is what happened. And on the Bermudan option, it's the same. It's really the same thing, but in a more complicated setup. And I invite you to read everything about it in the notebook. So you see, the problem with PCA fundamentally, it's not only with PCA, it's with any type of algorithm that's one size fits all. I don't care about the transaction. I don't care if you're trying to do a basket option, an option on basket. I will do the same thing. When you're one size fits all, in other terms, when you're completely unsupervised, well, bad things will happen because, for instance, if you're only looking at the states, you're never looking at the labels, then you know nothing about the transaction, its value, its risk, its payoff, its cash flows. You don't care about any of that. But if you don't care about any of that, it means, for instance, that you will do the exact same thing, whether you work with a basket option, which we said repeatedly is really a one-factor problem, at least under the Gaussian assumption, or say a basket of options, a basket of single stock options, which is not a one-dimensional problem. In general, dimension is not reducible to one. So you can see that you have to do different things in these two examples, but PCA will do the exact same thing. Now, more worryingly, we saw that PCA is unsafe. On two different examples, we saw that PCA told us it was okay to truncate where it wasn't okay at all. So PCA truncates, may well truncate, very relevant coordinates. That's when relevance doesn't align with variation, and relevance doesn't have to align with variation. You'd be extremely lucky if it was the case. And because PCA is one size fits all, and any one size fits all truncation is unsafe. Right? Suppose that I'm a very tricky hedge fund, a very aggressive hedge fund, and I know that you're doing some kind of truncation that's one size fits all. So I reverse engineer your truncation and I design a derivative which has value only in the truncated space. Right? Of course, as long as it's one size fits all, it has to be unsafe. So the only way to reduce dimension safely is to do it in a supervised manner. That's for sure. And so PCA, you should never use PCA like this. And I know we repeated it quite a bit of times, but you know, I've seen PCA used in this context over and over again, and that's just wrong. You should never do it. And in fact, we will propose an alternative which is guaranteed safe, effective, and efficient, which we call differential PCA, and we will show you why it's guaranteed to be safe in just a few minutes now. First, I want to quickly explore feed-forward neural networks. So artificial neural networks, these are constructs that generalize the notion of regression because unlike regression, they don't regress on a fixed set of basis functions. You don't decide upfront what is it you are going to regress on. They will learn these basis functions from data and encode them in their hidden connection weights, hence bypassing the curse of dimensionality. So I absolutely don't have the time to get into feed-forward networks and the feed-forward equations. They are covered in tons of literature, and I guess all of you are very familiar with those. So I just reproduce the feed-forward equations here. They are very classic. So in my notations, GL is the nonlinear activation of layer L. That's a scalar function that's applied element-wise, like ReLU of soft plus, which is a smooth version of ReLU. And my learnable parameters, theta, these are all the connection weights W, capital W, and all the bias B. And this is called the feed-forward network. It's a particular case of an INN. Sometimes they're called multi-layer perceptrons or MLPs. And again, I hope you're familiar with this. Otherwise, you have tons of literature everywhere. But I just want to show you classic representation of a neural network here. And what you can see immediately is that the number of connection weights, so the number of parameters, that you can see in this picture immediately, it only grows linearly as a function of the dimensionality of the inputs, because X is fed in the input layer, and you can see that if I increase the size of the input layer, but I leave the rest of the architecture unchanged, then very clearly the number of connection weights increases linearly and not polynomially. So hence escaping the curse of dimensionality. That's why these things work, yeah? And note that the output layer here is special. First, it's scalar, and second, it's generally not activated. What this means is that this output layer, this is its equation, yeah, that's just a linear regression, but it's a linear regression on the last hidden layer 4 in this example, in green, yeah? And when you look at each one, so each of these 3 units, what are they? Well, you can consider this unit, for instance, as the head, as the output layer of a subneural network. Yeah? Each one of them are the outputs of a subneural networks, and we have seen that these neural networks are universal approximators. So there are all universal approximations of some functions of X. So in this case, I have 3 units in my hidden layer 4, and each of them is a certain function of X, but it's a learned one because it's subject to learnable weights, you see. So here I don't decide what are my basis functions. I can't fix the units of a hidden layer 4. I just decide how many of them I want. So here I decided I want 3 in this picture. And then it will learn the 3 best from data. And what does it mean, the 3 best? Well, the 3 that I need to minimize the MSE, of course. So that's how neural networks work. You train them by finding the set of weights theta that minimize the MSE as usual. And they're generally trained by gradient descent, where you make small steps in the direction opposite of the gradients on many iterations, or you can have more effective variants, you know, like SGD, RMS prop, ADAM. These are all kind of smart heuristics, variations of gradient descent that work well in many practical cases. And you have a guarantee, by the way, modulo how you schedule your learning rate lambda here, of finding a local minimum, but finding the global minimum, it's a non-convex problem, and it's a known NP-complete problem, by the way, as a parenthesis. So the point I want to raise here is that you need to calculate these gradients somehow. And so you have a lot of weights, and so you have a lot of sensitivities to compute. And of course, these gradients, d MEC, d theta, were efficiently computed by backpropagation. And these are the backpropagation equations. Yeah? So again, I'm not going to review the backpropagation equations now. I would need 2 hours for that alone. But they are covered in a vast amount of literature, so including some presentation and courses that I gave and made available online, and you have all excellent tutorials by other people too. I mean, I just want to, I just copied the backpropagation equations here because we will be using them in a bit, okay? And that's backpropagation. It's the most critical technology in deep learning. It's what makes it work, really. And so, yeah, it's explained in depth in many books, classes, tutorials, and so on. And I have to assume that you're familiar with this, and I think you are. So let's look at the performance with our friend the Gaussian basket, but this time in dimension 30. It's the predictions of the NN versus the correct formula on an independent test set, as usual. On the left picture, I have 16,000 examples. Here I trained with 65,000 examples, and here with 130,000 examples. And you can see that they converge as they should. And that, again, you can reproduce by yourself in differential ML TF2.IPYNB on our GitHub repo. So dimension 30 is out of reach for regression. And ANNs appear to have no difficulty, but you can also see that they consume a vast number of training examples, that in particular in this simple example, we needed 130,000 something examples to find a decent approximation. And this is actually completely confirmed in literature, in finance or elsewhere. It's well known that neural networks work really well, but you need to feed them large number of training examples. And this is perfectly fine for offline learning. Blanca did that, Maggie did that. They trained on millions of price examples and they found very accurate approximations. And that's fine if you do offline learning, but I want to do online learning. And for online learning, this is not going to fly because I can't afford to simulate 100K plus examples. I need to get away with something like 1K to 30K maximum. And so even deep learning, you see, doesn't make the cut for me. And it gets worse because here I looked at how well prices are approximated, but of course we care very much about risk sensitivity. So by differentiation of a price, I can look at the risk sensitivity and compare to the correct one. So here, because I have a basket in dimension 30, here I'm looking at the delta with respect to the first underlying, okay? And I see that it kind of converges, but you can see, right, that it's a lot worse. Deltas are a lot worse than prices. And actually, that risk sensitivity is also converged. That's guaranteed by a variant of a universal approximation theorem, and Blanca explained it in detail in her presentation and her paper of 2 years ago. But what we can see is that they do converge, but they converge slower than values, and approximation is generally worse. And of course, risk sensitivities are super necessary. I had a discussion with one of my friends from a major hedge fund yesterday, and what we concluded is that, you know, the only reason we need the pricing formula is to differentiate it to get the risks. It's almost an intermediate calculation here. So we care very much about the risk. So this is not good news for us. And let me show you a real-world example, an autocallable best of 4 in Danske Bank Superfly with 4 local correlated local volatility models à la Dupire. So we're in low dimension here. Dimension is only 4, but it's a complex model and complex instruments. We used 32,000 training examples, and we have a decent approximation of values. But look at the delta. That's the delta with respect to the first underlying. It's basically random, right? So that's bad news, but we shouldn't be surprised really, because it's well known in the field of function approximation. The derivative of a good approximation is not a good approximation of a derivative. So here I have a stupid example that I compiled in 2 minutes on Excel. So you see the red curve is a good approximation of a blue curve, right? It's very decent. But the derivative of a red curve here is not at all a good approximation of a derivative of a blue curve. So that's very well known. But what's maybe just as obvious, but maybe less quoted, I don't know, is that conversely, the integral of a good approximation, if it's unbiased, is actually a good approximation of the integral. So it doesn't go both ways, you see, because here I integrated my stupid example, and you can see that the two curves fit really well, much better actually than the value itself. And that tells us something, right? It's why are we learning prices and getting poor deltas? Shouldn't we instead learn the risk sensitivities? And that will give us good prices by integration, yeah? Well, hold that thought. First, a conclusion, we established kind of a formalism for things that you already know very well, so I didn't pretend to say anything new so far. We just kind of formalized what it means to price by ML, reviewed some conventional ML algorithms. We saw that regression, well, really is only applicable in low dimension. Never do PCA. And ENN is fine, but you need a lot of training examples. And we had a hint by inspection of derivative sensitivities that maybe we should learn these derivatives instead. And this is, of course, the main promise of differential machine learning. So now it gets new. We are shifting gears. And Brian, all yours for differential machine learning.
Yeah. So now we're starting on the new stuff. And what is the differential machine learning, and how does it help? Let's see. First, remember that we're given a model X with inputs X and a derivatives book that and then we define the pathwise payoff. Y is a function h of x, and the randomness w. Then we compute our data set, the realizations xi and yi, and we do that, repeat that m times. So then we learn the function v of x, which is a conditional, or the value function, which is a conditional expectation y given x, and we learn this function alpha by minimizing the mean squared error. So that was the setting that we are in before. And now we want to introduce the differentials. And that's what we call differential data set. So for that, we want the pathwise differentials. We call those set I, and that's dh dx. And this is a vector in Rn, where n is the number of input states in the vector x. And then we learn the risk function by minimizing the mean squared error over gradients instead. So dv dx is almost d alpha dx, where we minimize the least squares. And as a byproduct, as Antoine mentioned, we can get the value function by integration. So the pathwise differentials, those were the set I, which is a vector in Rn. And we calculate these by bumping the initial variable x, so bump it by dx. And then we keep the randomness fixed, and we get a different payoff on this bumped path. And in a Black-Scholes model, we would have for a call payoff where the x cap t is the exponential of the randomness and times the initial state. Then we differentiate the payoff, which is the indicator function, times dx t dx, which is, again, xt divided by x. And again, we can do the exact same thing for the basket, where the basket has this call payoff again, and we see the simulation scheme for the basket here, and then we differentiate with the x. And in both cases, we can see that the payoff H and the derivative DH are computed efficiently together because a lot of the computations are actually the same for the two. And how do we compute pathwise derivatives? Well, in the general case, the derivatives of an arbitrary function h are computed with AAD. AAD was called the holy grail of sensitivity computation by Greevank. And it is extremely efficient. It computes differentials in constant time. So hundreds of sensitivities of some function h costs, say, something like 5 evaluations. So it's also very accurate because the sensitivities are computed analytically. But the AAD has a steep learning curve, so both in theory and in practice. It relies on computation graphs. It uses advanced programming techniques like operator overloading and expression templates. It's memory intensive, so memory management is critical. AAD was introduced to finance by Giles and Klasserman's Smoking and Joints in 2006. And because of its critical importance in finance, it is covered in a vast amount of literature, books, articles, tutorials, and blogs. And it also have implementations in many libraries, commercial ones like Compatible, NAC, and Matlogica.
We have the founders of Matlogica in the room, actually.
Yeah. And also, again, there's a book I've been told.
Yeah, so.
By Antoine. And, but we don't cover that much here. So.
If you want to have a look, you can pass it around.
So, Antoine also has a
yeah, but yeah. There's also the blue one. It doesn't cover AAD, but it's been co-authored by Jasper Andres, and then no, scripting is an important technology, sir. If you can pass it around, please.
And Antoine is also on YouTube with a video that you can watch. And of course, there are many other authors to this subject. And not at least Giles and Klasserman's seminal paper. So, pathwise differentials, do they actually exist? Well, let's see. So, we have a model with the F is the model, and it has an initial model state and some random numbers. That gives us the path. G is a transaction, and then the initial transaction state and the path coming from the model, that gives us a payoff. So the differential, the pathwise differential with respect to the model state, that is df dxm and dg df. And this one is fine, the model one is fine, but the other one with the payoff, there may be some problems with that, because if it's a digital, then it's discontinuous, and we can't really differentiate that. So that's not too good. But this is a well-known problem in finance, and it's not just a problem for differential machine learning. It's also a problem for Monte Carlo risk, and so the industry has developed a solution for that, and that's called smoothing. And smoothing is to approximate the discontinuous product by a close one that is continuous. So, for instance, for a digital, you would use a tight call spread. For a barrier, you would use a smooth barrier, or you could, again, read the blue book, or Antoine also had a presentation on the fuzzy logic 5 years ago at QuantMinds. So, back to existence. Here we will assume that the cash flows already have been smoothed, so thereby they do exist. And if we recall the pricing equation, we just integrate over the randomness, and yeah, that's the pricing equation. If we differentiate under the integral sign, then we get the risk is just the integral of the pathwise differentials. So now recall that the prices are correctly learned by minimization of the mean squared error. So we can do the exact same thing for the risks. So the pathwise differentials can be used for that. And we can learn the correct risk function by minimizing the mean squared error in the exact same way. So d alpha dx is the predicted risks, dh dx is the pathwise derivatives. And then the differential ML will converge to the correct risk sensitivities.
Really?
Okay. So now we can actually learn the value function two different ways, by minimization of the mean squared error, of either the conventional way, where we take the least squared error between, minimize the least squares error between the payoffs and the prices. Or we can do it the differential way, where it's the pathwise derivatives and the risk that we find the least squares error between. But in practice, the best results are obtained by combining the two. So we use, here we will use the notation MSE bar, that's over the differentials, and the index J, that's for the jth derivative. And we combine all this into the same cost function, and a good default for the weighting of the different risk mean squared errors, that could be the ratio of the variances like suggested here. So what are the benefits by this? Differential ML learns solid Griegs, of course, because that's how they're constructed. And also they learn solid values by integration. Another way to see this is also that you can see it as you increase the size of your data set, because for every xi, you now have both a payoff yi and you have n additional derivatives zi. It's a bias-free regularization. So if we remember the standard regularization, we had a penalty for large weights. Here we have a penalty for wrong derivatives. And both of them reduce overfitting and variance. But the standard one introduces a bias. We do not introduce a bias because both of these converge to the same function. So we do not introduce a bias. There's in the standard regularization, there's a strong dependence on this lambda here. And that was why we needed the cross-validation and all that. Over here, there's no strong dependence on lambdas because it's, again, these MSEs, they will all converge to the same function. So there's not a strong dependence on the lambdas here. We'll see the performance later, but generally it'll have a far better performance with the differential ML. A fourth way of seeing this is that instead of just learning from one point, then we also have all the derivatives, so we kind of learn from the shape of the function. And that improves the learning a lot. And actually it's better than regular ML with where you use n+1 times m examples instead. So you kind of make the two data sets of equal size. Okay, back to Antoine.
Thank you, Brian. So yeah, Brian just exposed, I would say, the main theory, the main things about differential machine learning. What is it? What makes it tick? And why it works? So now all that remains is to show you how it plays out if concrete algorithms, starting with differential regression. So let's see our very first differential ML algorithm. So recall standard regression, we minimize VMAC. Regularized, we minimize VMAC plus a penalty from the size of a weight. And differential, well, this is actually not a differential regression equation. This is a general equation of differential machine learning, whereby we minimize the combined MEC between payoffs and values and between risks and pathways derivatives. And in all three cases, we have an analytic solution for the minimum of the MEC in the regression case, right? In the case where you have a fixed number of basis functions and your coefficients theta k are the coefficients of a combination that define your approximator. So this formula looks new, but you know it's like the regularized formula. It's an extension of the well-known normal equation here. So here the CGG phi is the covariance matrix between the basis functions, so in size k times k. So it's the expectation of phi g transpose, where each phi j here, that's the vector in size k of all my basis functions, their derivative with respect to xj, the number j state variable. So when you review these slides at home, I'm just showing you here what these notations mean and how they play out on a cubic regression in dimension 2, so you can make sense of it by yourself. And this CG phi z here, CG phi z, so that's a vector. That's the vector of covariances of this phi j here with zj, which is our pathways derivative number j. And all these covariances are, of course, estimated over the training set. So, and the proof is very easy. I mean, this is easy, believe me. I know it doesn't look like it because it's notationally heavy, but it's just about notations. There's nothing hard about it. Believe me, when you look at it at home, you will get it in 5 minutes. And the proof is even easier because in all cases, it's a convex problem. So you just set the gradient of cost with respect to theta to 0, and the equations basically write themselves. So again, it's not hard, it's just heavy in terms of notation. And if you're anything like me, I catch these things a lot better when I read implementation code. And again, implementation code is publicly available on our GitHub repo, differential machine learning, applications, discussions of implementation details, etc. And this particular notebook is called differentialregression.ipynb. What about performance? Well, let's see our friend, the correlated basket. In dimension 3, degree 5 regression, only 1,000 training examples here, okay? So on the left, I have linear regression, classic linear regression, which we have seen already. On the center, I have the ridge regression, and I insist that it's been optimized by cross-validation, this one. And on the left, I have differential regression, as we just seen. And I think these charts speak for themselves. Why are they animated? That's because every second I change the randomness in the training set. The model remains the same, but I change the noise. And I see how my performance on the independent test set reacts to the noise in the training set. That's the exact definition of variance. And we can see differential regression, as promised, is very stable. Well, much better than the rest. And when I just increase dimension to 5, you remember this guy here? Ridge regression helps a little, yeah, but differential regression really performs better. And even in dimension 7, okay? So we could say we have a very sharp improvement of a ridge regression, even optimized with cross-validation. But you see, we didn't optimize anything with cross-validation. We kept the lambda absolutely constant. We kept it to default. So without any kind of cross-validation, we do better than ridge regression by cross-validation because, as Brian explained, it's a bias-free regularization. Still, I'm not happy. I'm not happy because it does deteriorate in high dimension. It looks good. It certainly looks good against standard and ridge regression, but it still looks a lot worse than even standard regression in dimension 1. And I'm not happy, you see, because I know from the maths that this basket is really a one-dimensional problem. My basket option only depends on the initial basket. It doesn't depend on the individual components of a basket. I know that it's a problem in dimension 1, and I want an algorithm that's capable of finding that from data. And as long as my algorithm is not able to see that from data, it's not good enough. So we're not quite done yet. We know that we can do better, and it should be possible to always safely reduce dimension to 1 in this problem, and it should be doable automatically from data, and then we can perform an effective regression in dimension 1, even if the original dimension was maybe 500 or more. And that's what differential PCA does. And that's a safe variant of PCA that gives you a safe and effective dimension reduction. So before I get into there, I must spend a minute on the notion of data normalization, because it's customary in machine learning to work with normalized data. So I always say, oh, we work with X, Y, Z, but it's not true. We don't really work with X, Y, Z. We work with a normalized version of X and a normalized version of Y. We subtract the mean, we divide by standard deviation, and by the way, we have already filtered out the constant or redundant columns, because otherwise we couldn't divide by a standard deviation of 0. What about Z? Remember, Z are the gradients of Y with respect to X. So Z is not just Z minus its mean divided by its variance. Z is, you can see immediately that it's the ratio standard deviation of X divided by the standard deviation of Y times the original derivative, okay? And this is actually critical when we work with risk sensitivities, because first, when I do my data normalization, normalization of X, normalization of Y, you see that all my risks are now expressed in consistent units. If you think physics, what are the units of my risk sensitivities? Well, you know, if it's a risk with respect to an equity, maybe it's in US dollars per equity points. If it's with respect to interest rates, it's maybe in US dollars per percent or US dollars per BP, depending on how I define them. And you see that it's not, I'm not going to be able to aggregate and compare all these guys, work with them all together. I need them expressed in consistent units. And we get that for free from normalization, because now all risks are expressed in consistent units of standard deviation of Y per standard deviation of X. And so they're good to aggregate. Note also that these risks now, my risks, are not just naked sensitivities because they multiplied by sigma x here. So, you know, in Black-Scholes, I have a big sensitivity to pi. Do I care about that? Do I sleep worse at night because I have a sensitivity to the number pi? No, because it doesn't move. It's a constant. So a risk, when we speak about the magnitude of a risk, it's not only the sensitivity, it's also times how much the things moves, and it's the same thing. It's just by data normalization, you see that the risks have been multiplied by sigma x. And now I can talk about the magnitude of the risks consistently and meaningfully. So after this little parenthesis, I'd like to quickly present differential PCA. That's the subject of our paper in Risk, printed last month with Brian, axes that matter, PCA with a difference. So recall our very simple example. X1 and X2 are two correlated assets, and I'm looking at a spread option written on X2 minus X1, and we say, oh, but PCA projects data on the blue axis, the axis of principal variation, and scraps the coordinate on the red axis because it has so small variation, but we saw that all the action, that is the magnitude of a gradient, happens actually on this red axis, and there's no action at all on the blue axis because the projection of a gradient, the coordinate of a gradient, the directional derivative is 0, so this coordinate doesn't matter at all. And so that tells us that the variation, the magnitude of the data coordinates, is just the wrong metrics for our problem. What is the right metric is something that we call relevance, and that's the magnitude of directional derivatives. When directional derivatives are 0 or epsilon, it means that nothing happens on this axis. It means that you can safely scrap it, you know. And so what we are going to do is what we are going to align the coordinate system with the gradients, not with covariance, but with the gradients, and scrap the coordinates where gradients are 0 or very, very small. And we will actually locate points by their coordinate only on the axis where gradients matter. And maybe I'll be very far. You see, I'm very far here. The projection of this guy is here. It's very far in space, but it doesn't matter because as far as my spread option is concerned, this guy and this guy are actually the same state, which means it corresponds to the same initial basket. So, you know, and this is very different in this example. Of course, this is, I did it on purpose, this example, where differential PCA and PCA do the exact opposite thing. In general, it won't be opposite, but it doesn't have to be the same thing, unless you're very lucky. Because differential PCA works with this notion of relevance. The relevance of the axis is the magnitude of the projected differentials, whereas PCA, the classic one, works with variation, which is the magnitude of the projected coordinates. Otherwise, the two do the exact same thing. Differential PCA is just PCA on differential data. It's that simple, right? Instead of working with the eigenvectors of Cxx, the covariance matrix of my x's, I work with the eigenvectors of Czz, the eigenvectors of my z. If you remember, z is the gradient of y with respect to x, so it has the same dimension as x, this is the covariance of the gradients and not the covariance of the original data. And so we are going to build a coordinate system where the gradients where coordinates of the gradients are orthogonal, and we are going to extract the axes of principal relevance, the ones with the highest eigenvalues, which are the axes that matter because they have strong magnitude, large magnitude for the directional derivatives, and we are going to truncate the axis where eigenvalues are negligible, where the sum is less than a certain threshold epsilon, whereby we will be truncating only axes where there is no action at all, where the directional derivatives are as good as 0 everywhere. And that will give us, of course, like in PCA, a method for doing low-dimensional state encoding. And the last line is just to recall that you're changing the definition of your data now. You're projecting it in a lower dimension subspace. And so you need to recode your gradients. You need to modify your gradients accordingly. This is a simple linear equation, but you must do it because, of course, otherwise you can't. You need the gradients with respect to the new variables in order, for instance, to do a differential regression in the projected space. So, differential PCA is PCA on differential data. The mechanics are really, really simple, but the power of it comes from two theorems. One is guarantee of safety, and the other one is guarantee of effectiveness. So let's see what it means. What's this safety guarantee? The theorem that we prove in the paper is the magnitude of the risks that you're truncated by dimension reduction is bounded by epsilon. Maybe you think I'm just overstating a trivial result, what this guy is talking about. Of course, by construction, it is the case. This is a trivial result. Well, it's not that trivial, you see, because we don't work with resensitivities. We work with pathways derivatives, which are not the same thing. And what the theorem tells you is that the magnitude of the truncation in the real risks is still bounded by epsilon. So if you denote delta, the true resensitivity, dVdx, then the theorem tells you that the magnitude of the truncated deltas is less than the magnitude of the truncate pathways derivatives, which is itself by construction less than epsilon. And recall that these magnitudes are meaningful because by normalization, they kind of include both sensitivity and volatility of the underlying. So differential PCA is guaranteed safe. It cannot, by construction, truncate any information that's relevant for the instrument in the model. The gradients of the deltas by construction, the magnitude of the truncated deltas in the error space will be below your threshold epsilon, which expresses the notion of acceptable risk. What about effectiveness? So first, I want to show you that we finally resolved this problem, this basket problem that has been nagging us for 2 hours now. Suppose that h, my function h, you remember my payoff function, that it's a nonlinear function of only one linear feature of x. So that h has this form, h of xw is some nonlinear function beta of A transpose xw, where A is a fixed vector. That's what it means, okay? So we can see immediately that it's the case in the basket option under the Gaussian assumption, because recall the h function in this case has this form here. We derived it earlier, and you can see that it's a nonlinear function of a linear feature of x. So this is a particular case. So what happens then? Then you can use the chain rule to find the derivative z, dh dx, and that will be d beta datx times a, which I choose to multiply and divide by the magnitude of a, and I finally find that it's this guy, which I call gamma tilde, times this guy, which I call a tilde, and importantly, gamma tilde is a random scalar. It's random because it depends on w, and it's a scalar. It's a real number. It's not a vector, whereas a tilde, which is the unit vector a, that's a vector. It's a unit vector, and it's deterministic. So when I calculate my matrix, covariance matrix CZZ, the expectation of ZZ transpose, well, I immediately find that that's just the L2 magnitude of gamma tilde times A tilde transpose, okay, because the A is non-random, so it gets out of the expectation easily, and I find this form, and this is, of course, an eigenvalue decomposition, which immediately tells you that this CZZ has only one non-zero eigenvalue. The eigenvalue is the magnitude, the squared magnitude of gamma tilde, and only one, and the associated vector is A tilde. So what this means in English is differential PCA effectively reduces dimension to 1. It's able to tell you from the data that the dimension of your problem is 1, and it actually finds the future. It finds the future. It gives you your basket. It tells you what it is. And from data alone, so we finally resolved this problem. So you remember this picture, linear regression, ridge regression, differential regression, that was for a Gaussian basket in dimension 7. Now I have a Gaussian basket in dimension 500. And all I do is I pre-process my data with differential PCA, and only 1,000 training examples, and what happens, it's almost perfect with classic regression, it's perfect with linear regression, just like that. Of course, because effectively I'm doing my regression in dimension 1. But of course, I'm not always in dimension 1, so let's see what happens here. Well, every function h of x by trivial linear algebra, it's also a function of n linearly independent features of x. That's just by a change of variable. But very often, not always, actually I will show you a counterexample in a bit, but in most cases of practical relevance, you find that h is approximately a nonlinear function of only a few linear features of x. Not n, but p. P is less. So I say that h of xw is always a function beta of, you know, a1tx, a2tx up to antx. But actually, I can almost always find a lower number of features that matter. But it will be a nonlinear function of only p features and not n features. And then by a calculation that, you know, it's a direct extension of the one we just saw, which was trivial in dimension 1. Maybe it's a bit less trivial in dimension p, but it's really the same computations where things are not numbers but matrices. And you find that differential PCA, in this case, will find exactly p material eigenvalues. And the eigenvectors won't be your A1 up to AP, of course not, because eigenvectors have to be orthogonal, and these guys may not be orthogonal, but they will span the same space. And this is demonstrated in the paper. And in English, it means that differential PCA always finds the axes that matter, i.e. the relevant factors. So for instance, recall PCA does the same thing for an option and a basket, or a basket on options, but we saw that differential PCA always reduces dimension to 1 for an option and a basket. Whereas if you have a basket of single stock options where the single stocks are independent of the same volatility and all options are at the money, say, then dimension is simply not reducible because the relevance of all the axes, the relevance is equally weighted. So there's nothing to reduce there. And differential PCA will not try to reduce it. It's not reducible. Differential PCA will tell you that it's not reducible. However, in all the examples that we run in over a year with Brian, in all the practical examples, we always found that differential PCA reduces dimension by a vast amount. But of course, there's no theorem that tells you that it's going to always reduce dimension, because such a theorem would be wrong. I just show you a counterexample. But in practice, it is. So let's see how well it performs. Recall this graph. This is for the continuation value of our Bermudan option in the 5-factor model. So you recall what PCA did. If it reduced dimension even by only 1, you got a lot worse. Yeah? You recall this graph? That PCA was not able to reduce dimension safely. So let's see what how differential PCA plays out. So now we don't have an explanation of variance, we have an explanation of relevance over principal component. Component 1 explains 99%, component 2 almost 1%, 3, 4, and 5 explain nothing. So now differential PCA tells me that it's okay to only consider component 1 and 2 and truncate the 3 other components, which is something that Jasper and Leif told me 20 years ago in a famous paper, Factor Dependence of Bermudan Option, Fact or Fiction. They found by analysis that Bermudan options are sensitive to 2 factors. And here I find the same thing by differential PCA. I would have been very worried if I didn't. And again, you have sources on GitHub here, bermudan5f.ipynb. And how does it perform? Well, this is the one on raw data in dimension 5. You have a classic regression in blue and differential regression in whatever, in pink. And here you have something but on projected data. And you see that safety works. You didn't lose anything. In fact, it works a lot better. Well, the classic regression works a lot better because now you're in dimension 2. Differential PCA, differential regression doesn't really care. 2 or 5 is pretty much the same thing. But the point is, I effectively truncated my dimension to 2, and I didn't lose anything at all, right? Only irrelevant information was truncated in this case. One word about efficiency. What's the development cost? If you're going to develop differential PCA, what does it cost you? Well, nothing. It's an immediate dropping replacement for PCA. You can see the code in our notebook. It's also a PCA, just on a different data. So as long as you have a differential data and you have it with AD, it's 0 cost. What about runtime cost? When you need to compute the covariance matrix CZZ, we computed it on a high-performance library like MKL, 32,000 example in dimension 1,000. It's done in 1/4 of a second. Then eigenvalue decomposition For a symmetric matrix of size 1000, MKL does it in 50 milliseconds. So it's all zero by RISC standards. And so the conclusion is differential PCA is PCA on the covariance of the matrix of the gradients, CZZ. It's a very simple deployment with basically zero runtime cost. It's got this guaranteed safety that tells you that it will never truncate meaningful information, modulo, of course, your user-specified acceptable risk threshold. Epsilon is designed to extract the linear features that matter. The applications, as we saw, safely reduce dimension, for instance, for regression. It's also super useful for neural networks. Neural networks are immune to the curse of dimensionality, but still, they train a lot faster and in a lot more stable manner in lower dimension. And since you can do it virtually for free and with safety guarantee, there's really no reason not to do it. And there are some further applications which I don't cover in this presentation, but for instance, identify the regression variables in LSM. That's kind of a loose end that's with LSM, that's been with us for 20 years. LSM is a regression, but what is it you regress on? What are your regression variables? And usually in most implementation, it's more or less clever guesswork. But if you think about it, differential PCA gives you the answer. Immediately, it just gives you, it tells you what you should regress and what are the axes that matter. So it nicely ties up a loose end that's been with us for a while. Reliably exhibit the risk factors of a given derivative instrument or training book, hence help us correctly specify and calibrate risk management models. And we are almost done, and miraculously will be done on time because it will take just 5 minutes to Brian to present the last differential algorithm, arguably the most powerful one, which is differential deep learning.
Yeah, as Antoine said, this is the last part of this talk, and it's how we're going to use neural networks in this differential machine learning setup. And this was the subject of our paper last year in Risk Magazine, Differential Machine Learning, the Shape of Things to Come. So recall that, that we are minimizing this cost function, both of differentials and values. And now our approximator is alpha, is a function, the function of theta is a neural network. And Antoine gave us the feed-forward equations before. And now we have the differential data set, x, y, and z. So we almost have all the pieces we need to perform training. The only thing that we are missing is this red guy up here. That's the risk predictions. So we'll see how we get those from the neural networks. Neural network in a picture. So you have the inputs, input layer in the yellow dots. Then you have the hidden layers. That's the white circles. And the orange one is the output layer. And then you have the feed-forward equations. And the alpha dx, that's the gradient of this value, the orange dot, with respect to the input states x. And how can those be calculated efficiently? With the backpropagation equations, of course. And again, we have the well-known backpropagation equations here, but we don't need the derivative with respect to the mean squared error. Instead, we need it with respect to the value v, so we can skip that one. We don't need the derivatives with respect to the weights and the biases, so we can skip those as well. And we just need the differentials with respect to our inputs. So a little bit simpler backpropagation equations in this sort of setting, or for this purpose. And we have used the notation with the adjoint notation, where you have a bar over something, and then that's dv something. And again, we have our network. and with the back propagation equations that starts from dv, which is 1, and then go back to the through the back propagation equations, and then the output from this is the sensitivities with respect to the inputs. Oh, there we go. And in the 1990s, ML legend Jan LeCun, he noticed that the back propagation equations define a dual network. LeCun did not do anything with that, but in finance it actually makes a massive difference. We can concatenate the original and the dual networks into something we call the twin networks. And that means that we are capable of predicting prices and risk for just twice the cost of price alone. So we can train the twin network efficiently, and now we have both the alpha and the d alpha dx coming from the twin network. And that means that since we now have one network that produces everything for this one, the cost function, then by another layer of back propagation, the original back propagation equations, we can optimize this twin, the whole twin network at once. Yeah. And afterwards, the twin network can be used to compute prices and risk efficiently. And to see how that works, again, the network, and with a twin network, it looks like that. Wow. Yeah. You have your inputs, the feed-forward equations, the value prediction, the back propagation, and out comes the sensitivities on the right. The right part of this network, which is this one, is a mirror image, and it has some dependencies to the original network. One of those is that the two networks, they share the weights. So when you differentiate the left network, you have the same weights in the right network. Also, the activation functions, they become the differentials of the original activation functions. And if you look really closely to the slides, you would see that the activations over here are soft plus, and over here they are sigmoids. Very fancy. Yes. And again, it may be better understood with implementation code, and we have it on GitHub, as mentioned once or twice. And I'll leave you with this last example. This is, again, the left part of this is the autocallable example from our first paper. And the cyan dots, that was the ones that you saw from the classic network. And it was trained on 32,000 examples. The purple dots that line up right on the 45-degree line, that's the differential network. And it's only trained on 8,000 examples. Also, for the derivatives, we see now we are actually getting something that looks like a 45-degree line. And again, it's only trained on 1/4 of the examples that the classic network is. On the right, over here, we have a picture, same sort of picture. It's just for a real live netting set from Danske Bank. And we have trained in the cyan dots, we have trained the classic network with 64,000 examples. And we have trained a differential network, the purple dots, with only 8,000 examples. So 1/8 of the number of examples. And still it outperforms the classic network by orders of magnitude. Then we're thinking about writing a book.
Yeah, I expected that we would have signed the contract by today, but it's still in the air. But there's a good probability that the contents of this presentation will be printed as a book, expanded and printed as a book with Chapman and Hall in the coming 6 to 9 months.
Thank you for your attention.